Alright, we gotta talk about strong acids, strong bases, weak bases. So hopefully after this, we can identify strong acids and bases and predict products of strong acids and weak acids, and strong bases and weak bases. So the strong acids and bases, those dissociate 100% of the time in solution. So that means that all of the hydrogen ions separate from all of the negative ions. The chlorate, the chlorine, the bromide, the iodine, the nitrate, all of it. And the same thing with the bases. All of these hydroxide ions dissociate from all of the metals. Our lithium ions, our sodium ions, potassiums, all of them. And you guessed it, the weak acids and bases do not dissociate 100%. This could be 10%, this could be 20%, depends on what you're working with. And because they don't dissociate 100%, there's less hydrogen ions, there's less hydroxide ions floating around, our pH doesn't change significantly like it does with the strong acids and bases. So here's a picture of what's going on. Here we have our combined compound, and it looks about the same in both beakers to start with, but one of these is a strong acid and one of these is a weak acid. So in the strong acid, all of my particles have dissociated. I have all of these hydrogen ions, all of these acid ions, but very, very few combined compounds. Here it says none. That one kind of looks combined, so maybe there's a little bar right there. We don't know. Versus this one, I still have a lot of combined compounds. Let's see, these dissociated and those dissociated. And as we see, we have very few hydrogen ions and very few acid ions, and a lot of what we saw at the very beginning. And that's the difference between these strong and these weak acids. Our strong acids make lots of ions, and our weak acids don't. They stay together as they were to start with. And because we don't have a lot of hydrogen ions, that changes. Because when we don't have a lot of hydrogen ions, that doesn't change the pH a lot. And when we have a lot of hydrogen ions like we do with the strong, we see a huge change in pH. It becomes much more acidic. So take a minute, what's the difference between the strong acids and the weak acids, and the strong bases and the weak bases? You can go back if you need to double check yourself. So even our reactions and how we write them is different. In our strong acids and bases, we see this forward arrow indicating that these products on the right are the only products. Versus on the weak side, we have a double-headed arrow, which says that these are products, but sometimes the reaction goes backwards and we get these as products. So all of these are possible products. Again, indicating that these ions or these acids dissociate 100%, whereas the weak ones, sometimes you get ions, sometimes you don't. Now here it is in words again, just in case you haven't gotten it. Because the strong acids fully dissociate from their hydrogens, there's a huge decrease in pH. They get much more acidic. And that's the flip side with bases. You see a huge increase in pH, because remember, bleach has a pH of 12. And these basic compounds have these huge these huge pHs, low concentrations in hydrogens, because they have an inverse relationship. The weak acids, since they don't fully dissociate, there's a baby change in pH. There's a little bit of a change, but not a huge change. And here it is if you're a visual person compared on the pH scale. Strong acids, low pH. Strong bases, high pH. And the weak are closer to neutral. And when you're dilute, you have lots of water. When you're concentrated, you have lots of solute. So let's think about this on a particle level. Which box has a higher concentration of hydrogen ions, and how does this change the pH? Let's see, the box on the right, there's only this hydrogen right here. So when my hydrogen concentration is low, my pH is high. This one has a whole bunch of hydrogen ions. And when I have a lot of hydrogen ions, my pH is low. I'm super acidic. So this difference in hydrogen ion really changes our pH, and makes a huge difference when you're working in an industry like cosmetics, because let's say I have a lotion and the pH is too basic for what I'm working with. Well, if I only need to change it a little bit, I would want to use a weak acid to bring my pH down a little bit. If I needed to change my pH a lot, I would add a strong acid to bring my pH down a lot. It just depends on what you're trying to do. So now we gotta think about, how is the strength of an acid different from the concentration? So we already know that the strong acid and the strong base, or the strong acid and the weak acid, has to do with the hydrogen concentration. But concentration itself, the molarity, has to do with the number of particles overall. Here we have a whole bunch of particles where we're concentrated, but when we're dilute, we have very few particles. Now the diluted acid and the weak acid, now those do not look the same, because in the weak acid I still have compounds that are together. In my diluted strong acid, I still don't have a lot of compounds together. I still have a lot of hydrogen ions. Just I have a lot more water. So let's say that this pH is 2 because there's lots of hydrogen ions. This pH might be 4 because we diluted it. We added a bunch of water, which pulled that pH closer to the pH of water, closer to 7. So diluting an acid with water is different from having a weak acid, because in a dilute strong acid you still have lots of hydrogen ions, versus dilute weak acid you don't have as many hydrogen ions, you have more acid ions. So how is pH affected by strong and weak acids? If you need to go back and check, go back and check. So let's say we have hypochlorite acid mixed with water. We want to predict what's going to happen to the pH and give a balanced equation. Let's see, hypochlorous acid. That's not a strong acid. So let's see, if we go back to nomenclature, chlorus comes from chlorate, which is ClO3. And then we're mixing it with water. And we have hypochlorous acid. This H is going to want to leave the acid. But because it's not strong, sometimes the equation will reverse. So we'll have some chlorate ions and some hydronium ions, but sometimes we'll still see these. And we'll see a weak change. If you ever see a triangle in front of something, that means change. It's also called delta, change in pH. Let's see. 3 hydrogens, 3 hydrogens. There's a 3 oxygens, 3 oxygens. We're balanced. We're good. So now let's see what happens if I have hydrobromic acid. This one right here, which is a strong acid. If I mix it with water, we're going to have full dissociation. So my hydrogen's going to go hang out over here. And I'm really not going to see a whole lot of my products. So I'm only going to put the 1 arrow. And we'll have hydronium on the end. pH goes way up, goes way down. Because we're adding an acid, we see a huge decrease in pH because it's becoming more acidic. So if you're an acid, you just want to say if you're a strong acid, just shut up and take my hydrogen ions. The bases are a little bit different, so we're going to go through this one. So let's say we have lithium hydroxide, this guy right here, and we're going to mix it with water. And we have lithium hydroxide, and we mix it with the water. Well, lithium hydroxide is a base, so the base is going to want to take up a hydrogen. So this hydrogen right here is going to want to go hang out with that hydrogen over there. Well, because this water right here loses a hydrogen, we get some OH ions. But we're not just going to stick a 2 right there, because that's not what happens. When we stick lithium hydroxide in water, we start seeing lots of bubbles because we have this huge reaction. And we start to see hydrogen gas and more lithium ions. So this hydrogen gas is the bubbles that we see. But we still see an increase in these OH ions due to the water losing the hydrogens. And as we know, if we have lots of OH ions, our pH is very high, very, very basic, because we have very, very few hydrogen ions, because they all got taken up by the hydrogen gas. NH3 on the other side, ammonia, is a weak base. If we mix that with water, sometimes it'll take water's hydrogen and we'll get NH4 plus because that nitrogen can take on another hydrogen. But sometimes the reaction goes back and he gives the hydrogen back to the OH because it's weak, and sometimes they fluctuate back and forth. So our pH is going to go up a little bit. Not a whole lot, but a little bit, because sometimes it'll be high, sometimes it'll be low. So our strong acids donate all the protons, all the hydrogens. But just because hydrofluoric is a weak acid doesn't mean it's not dangerous. If we look, our hydrofluoric acid, it took all the color out of that chicken bone. Every single bit of it. All the blood is drained from that chicken bone. I mean, the hydrochloric acid kind of liquefied everything, and the hydrosulfuric acid practically did weird color change and melting, but that hydrofluoric acid is just as dangerous. So here's your exit ticket. When you're done with it, just send me a picture so that I know that you did the assignment.